Okay, in this problem, we have a 1,500 kilogram car skids to a halt on a wet road where mu k, the kinetic coefficient of kinetic friction, is 0.5, and it wants to know how fast was the car traveling if it leaves 65-meter long skid marks. Okay, so the first thing we want to do is draw a picture. So I'm going to draw a road and then a car. It's starting, let's say this is x equal to 0. It ends up over here at x final. And it's moving this way. So let's write our givens and finds. So we're given that the mass of the car is equal to 1,500 kilograms, that the mu k is equal to 0.50, and it says that there's 65-meter long skid marks. So that means the car is going at a certain speed here at the start, and then it goes all the way till an X final position, and there's skid marks on the road from skid marks from here all the way to here. And so that means our X final is going to equal to 50 meters. So that's the first thing we want to do with our pictures. Let's draw our boundary. So we'll draw a boundary. And let's take and do a different color. So we're going to do our force of the normal, right, is going to be up. So the force of the normal is on the tires. We have the force of gravity, which is going to be down. Force of gravity. And we have the force of friction. So we know the force of friction is going to be against the motion, so it's going to be this way, force of friction. So imagine you step on your brakes and you lock up your wheels so they're not rolling anymore. They're locked in place and they're sliding, and you're sliding on the road. Okay, so what we want to do now is we want to take the forces that we've identified from along our boundaries. So remember, we were doing contact forces, and those would be the force of the normal up on the wheels and the force of friction. And our long range force is the force of gravity. So let's do a free body diagram here. Force of the normal, force of gravity. Now this car is not moving in the y direction. It's not going off the road. So these two arrows are equal. And the force of friction is this way. So this tells us we have a net, so an F net that way, which means we have an acceleration also that way. All right, so now let's take our free body diagram, and that way we can create our equations for Newton's second law. So Newton's second law says the sum of the forces in the x direction. And since we have a net force, we know we're going to have mass times acceleration. Remember, the sum of the forces only has two, it's only equal to two things, 0 or ma. And so if there's a net force, we have ma. If there's no net force, then we have 0. So the only force acting in the x direction is the force of friction, equal to ma. And we know that mu k times the force of the normal is the force of friction. And we can find our force of the normal by looking at the free body diagram and figuring out what our components are in the y direction. So, like I said, the car is not going off the road upward. So we know, since it's not moving in the y direction, we know that our sum of the forces in the y direction are equal to 0. So we have up, the force of the normal is up, so that's positive, minus force of gravity, which is down, is negative, equals 0. I'm going to solve for the force of the normal, so I'm going to add force of gravity to both sides. So my force of the normal is equal to force of gravity, and I know that force of the normal is equal to mg. So I can plug that in over here, and I get mu k times mg is equal to ma. And here I'm looking for a, because remember, I didn't write my find, so my find was find the velocity at the start. So velocity when the person first puts their brakes on. So I'm looking for a here. So I can cancel out my m's, and I get a is equal to mu k times g. And if I plug in our values, mu k is equal to 0.5 and g times 9.8 meters per second squared. So A is equal to half of 9.8, which is just 4.9 meters per second squared. And now I can use that to find my initial velocity. So I think in this case, since I have an acceleration and I have an x final, I'm going to use this equation. I'm going to say v final squared is equal to v initial squared minus 2a delta x. Okay, so thinking about my picture, or I can make a motion map from this. So I know at the start, when I first put my brakes on, I have a big velocity, right? So that's my v initial. And I'm slowing down, right? So this is going to be my x initial. This is my x final, right? And so I know when I end, my v final here is going to equal 0. So I go over here, this is going to equal 0. I'm looking for the v initial. I know acceleration, and my delta x is just my x final. So it's my delta x is x final minus x initial, but x initial 0. So this is going to be my delta x. So I'm going to plug that in. So now I want to find vi. So I'm going to add 2a delta x to both sides. And when I do that, then I can say vi squared is equal to 2a delta x, or vi is equal to 2a delta x square root. And plugging in my numbers, I get 2 times 4.9 meters per second squared times, I think it was 65, or no, it was 50? No, it was 65 actually. So 65, I wrote that down wrong. So let's fix that. 65 meters times 65. Oops. Take the square root, and when I plug that in, I get 25.2 meters per second.